reset. The math is simple. The Ergun equation shows that pressure drop is tied to the square of gas velocity. If the dp is erratic, don't wait, reduce the wind rate by 10% in two steps, 5% each. Now, this lowers the upward force, letting the internal layers settle so the material can start moving steadily again. We know a small particle cause massive problem. We call it a cubic rule. A teeny 10% decrease in space between material, that is voidage, can skyrocket your pressure drop by 300 to 400%. You must audit your stockhouse screen immediately. Fines smaller than 5 mm must be removed because they block the coke slits. The critical path gas need to flow through the high resistance cohesive zone. Sometimes the pressure problem is not at the top, it is at the bottom. If the iron and slag are not removed fast enough, they create an upthrust against the coke deadman. This upward force compresses the solid burden above it, making it much harder for wind to pass through. Then what is the fix? Ensure the furnace is cast dry without any delay. If one taphole is slow, open a second one immediately to drain the hearth. So we need to ensure that hearth evacuation there is no constraint or delay. Now the shape of your cohesive zone determine your stability. If it becomes W shape, gas is forced to the wall, causing head loads and pressure jumps. We want an inverted V shape to get the increased central coke charging. This creates a central coke chimney, gives the gas a stable low resistance path through the middle of the furnace. Now watch your thermal state. A furnace that runs hot with the silicon over 1% can actually become unstable. It raises the cohesive zone, uh, making the burden lighter and prone to hanging, where it stops descending. If the furnace is too hot, increase blast moisture or lower fuel injection to cool it down and keep the material moving, which is supposed to be our prime objective. Chemistry play a huge role in pressure control. If your slag is too thick, it floods the void in the coke and spike the dp. To prevent this temporarily, reduce slag basicity by 10%. Now this makes the slag more fluid at 1400 degrees centigrade, allowing it to pass smoothly through the concrete without blocking the gas flow. So now if the burden is still stuck, you may need a control check by briefing or by briefly opening the snot valve. You quickly remove pressure to break material breezes and induce a controlled slip to restart the movement. Finally, remember the safety limit. If dp stay above 1.8, the furnace is overblown. You must reduce wind and fix your burden quality to avoid a catastrophic slip or a chilled hearth. But the most important way out is we must have to choose at what DP furnace is stable. Now, if we have chosen lesser DP than our normal operation as furnace has a abnormality, furnace cannot able to sustain the similar DP, so we have to curtail the DP. Now, this reduction of DP must have to chosen very carefully, because reduction of dp is not the only way out. Reduction of dp up to a stable point is the way out. So if your furnace is at 1.8 dp and it is not stable, you bring it down to 1.6 through 1.7 experimentation, and even if it is 1.6 you find it is unstable, you need to reduce further. You must have to choose that delta p which remains stable in the furnace, and that is the only key. But if we just reduce the delta p, then our normal regime and start speculating improvement, it will take time. So choosing delta p, right delta p, and which signify by its stability, is the topmost strategy which is going to give us a result. This will also feed a lesser fines by the higher drag force to the deadman. Our deadman permeability will also improve, and re, automatic inside within the furnace generation of fines will be also taken care due to higher drag force due to unstable dp.